Hi everybody, this is Mrs. Mancuso. We're doing a little bit of chemistry review. Today we're going to talk all about gases. So first thing we have to know is that the goal of a gas is to always spread out. There are very weak attractions between them, so they don't want to be close to each other, they want to spread out. So what is ideal for a gas? Warm temperatures. When it's warm, the molecules move faster and spread out. And low pressure. If there's a lot of pressure, you're going to squeeze gas molecules into a small space. You want to let them spread out. So that is what is ideal. They also move in random, straight line motion. So they're pretty much constantly moving, but you can think of it like this is my particle diagram and I have all these little gas molecules all spread out. They would move in a straight line until they hit something, like they hit this wall, and then they start going into another. And so they'd be like boing, 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 like that, like the little screensaver all around. Some gases are diatomic. That means that there are two of the same atom together. So that's what oxygen looks like, or nitrogen, or fluorine, or chlorine, or bromine, or hydrogen. All right, to calculate a gas. Well, first of all, when you're talking about gas, we want to talk about pressure, volume, and temperature, because pressure, volume, and temperature all affect how a gas behaves. So pressure is going to make a gas occupy a smaller space, and that's because gases are compressible. Solids are not compressible and liquids are not compressible, but gases are. So you can make them be closer together. They would normally occupy all of this space in a container. So they occupy all of the space because they spread out. But if you put pressure, you're going to make them occupy a smaller volume. And so the volume is affected by pressure. So all three of these have an effect on each other. You could do a graph for each one. So pressure and volume have a graph like this, which means that if I'm at high pressure, I'm occupying a very low volume. And if instead I have low pressure, I would occupy a very high volume. I'd be able to spread out. If I compared pressure and temperature, that's directly proportional. So this was inversely proportional. This is directly proportional. As the pressure goes up, the temperature goes up, or vice versa. As you heat something up, there's more pressure because the molecules are moving faster and bouncing off of each other. And I could also do volume and temperature. So as I heat something up, it's going to occupy more space. So those are our three graphs. And then we have our gas law equation. So P1 V1 over T1 is equal to P2 V2 over T2. And I get that right here, combined gas laws. And it tells me P is pressure, V is volume, T is temperature. The temperature always has to be in Kelvin for this to work. So I could have a word problem. I could say that I have a balloon and that it is a 5-liter balloon and it's at standard temperature and pressure. And I want to know what is the volume if I, let's see, if I increase the pressure to 1.5 atmospheres and I decrease the temperature to 250 K. All right, so there's my question. So here's V1, T1 and P1. I have to use my reference tables. So I go here on the reference tables to table A, and I want to use ATMs because I know that later on they used ATMs for pressure. So standard pressure is 1 atmosphere and standard temperature is 273 K. All right, and then V2 is what I'm solving for, so that's my X. My second pressure is 1.5 and my second temperature is 250. So then what I do is I plug in all of these values. 5 times 1 over 273 is equal to V2 times 1.5 over 250. Okay, that would be my correct numerical setup. And if I had to solve, I need to keep going here. So I have 5 times 1 is 5 times 250 divided by 273 times 1.5 would equal V2. So there's my setup, and I can do the math. So I just have a little calculator here. I can't punch things in, so I got to go like that. I mean, I can punch things in, but I got to write it all down as I go. So 250 times 5, I get 1250, divided by 409.5 equals 3.05 liters. So there would be my answer. So that's how you do a gas law problem. And again, if you are given a question and it says, you know, that the temperature remains constant, you can just cross it off on both sides. You don't have to do it if it is there. So again, big things about gases, you just want to remember they always want to spread out. If you do a particle diagram, you want to draw them as separated as possible. That's because they have weak attractions between them. Their ideal conditions are high temp and low pressure. They move in random straight line motion, and they always occupy their container. Thanks for joining me.